You know that feeling when you sprint up a flight of stairs, trying to beat the clock? Your heart's pounding, your legs are burning. Well, it turns out you weren't just racing against time, you were actually running a pretty cool physics experiment. And today, we're going to break down exactly what was going on.
So here's the plan. We'll start with a simple scenario. Then we'll calculate the power involved. After that, we'll uncover some hidden energy you might not have thought about, and we'll wrap it all up with a surprising little comparison.
So here's our setup. It's incredibly simple, but it's perfect to what we're trying to understand. We've got a girl running up a flight of stairs just as fast as she can. That's it. Simple, right? But believe me, there's a whole world of physics hiding in that one simple action. Now, to figure this all out, we only need 3 little bits of information. We know her mass is 60 kilograms. We know the vertical height she climbs is 175 centimeters. And she does it all in just 1.40 seconds. I mean, wow, that is seriously quick.
Okay, before we dive into any of the fun physics equations, we have to do a little bit of housekeeping. We need to make sure our units are all on the same page. So the first super important step is to convert that height from centimeters into meters. 175 centimeters, that just becomes 1.75 meters. Easy enough.
All right, with our units all sorted out, we can get to the main event, calculating her power output. This is where we really get to see how much work she's putting in.
So what even is power in a physics sense? It's not just about being strong. It's really about how fast you use your energy. It's the rate at which you do work. The quicker you get something done, the more power you're generating. And we measure all of this in watts. And the formula for it? It's actually really straightforward. Power is just the amount of energy you transfer divided by the time it takes you to do it. This one simple equation is the key to unlocking this whole thing. Okay, let's walk through this together. First up, we need to find the energy she used. By moving upwards, she's literally fighting against gravity. So we calculate that energy by multiplying her mass, times g, which is the pull of Earth's gravity, always 9.8, times the height. So 60 times 9.8 times 1.75. That gives us 1,029 joules. Now we take that energy and we divide it by her time, which was 1.40 seconds. And boom, there's our answer. She generated 735 watts. To put that into perspective for you, that's almost enough power to run a microwave oven, all from just running up some stairs. But, and this is a pretty big but, this is only her useful power. So 735 watts. That seems like a final answer, doesn't it? Case closed. But is that really the whole story? Is that how much power her body was actually kicking out? I mean, think about it. When you exercise, you get warm, right? Where does all that energy you're burning actually go? Does every single drop of it go into doing useful work? So the real question is, why is her body's total power output actually way higher than the 735 watts we just calculated?
Well, the reality is our bodies just aren't 100% efficient. A huge amount of the energy from her muscles was actually just converted into thermal energy. That's the heat she feels. That's energy that's basically lost to the air around her. And then there's all the kinetic energy needed just to get her arms and legs moving. So that 735 watts, that's only the useful part that went into gaining height. Her body's engine was actually working much, much harder.
Okay, now let's make this even more interesting. We're going to throw a new puzzle into the mix. Let's bring another person into this scenario, a boy, who's also going to run up that same flight of stairs. And here is where things get a little weird. The boy took longer than the girl did, but his useful power output was exactly the same, 735 watts. So how is that even possible? So here's the puzzle for you. If he was slower, meaning his time was greater, but he ended up producing the exact same amount of power, what other piece of the puzzle must have changed to make those numbers work out? Take a second and think about that power equation. And the only way this can possibly work is if the boy's mass was greater than the girl's. Remember our formula? Power equals energy divided by time. If his time went up, he had to transfer more energy to keep the power the same. And since the height didn't change, the only way to increase that energy is to have a bigger mass to lift in the first place. And that's what's so cool about this. These physics equations aren't just for getting a number, they're telling a story. They're telling the story about the beautiful, delicate balance between mass, height, and time. So we're left with this thought. Physics isn't something that just happens in a classroom or a lab. It's happening every time you lift your groceries or ride a bike or even just get out of your chair. So my question to you is, What everyday things will you look at a little differently now, knowing about this constant, invisible transfer of energy that's happening all around us?